Hello children, good morning. One more time, this is my second video for you. Today I am going to describe about the reactivity of metals in a group, that is moving from top to bottom in modern periodic table. While we talk about the reactivity, then we must know the reactivity of metals in a period, reactivity of non-metals in a group also there, but today I am going to focus only the reactivity of metals in a group, that means from top to bottom in the modern periodic table. For this you must know what is metals are. In this perspective, metals means they are electropositive. Electropositive means they lose electron to get stable configuration. For example, potassium has one electron in its outermost shell. To get stable configuration, it loses that electron. And similarly, sodium, magnesium, aluminium, they all are metals, means they are electropositive. Why? Because they lose electrons from outermost shell to get stable configuration. Generally, metals are found in the left hand side of the modern periodic table. Children, you please see the modern periodic table here, and in this periodic table, this side is left hand side and this middle side, and here it is right hand side. And you can see the metals in left hand side of this modern periodic table. For example, beryllium, magnesium, sodium, potassium, calcium, strontium and barium, so on so on. And here this is also left hand side here, like you can see vanadium, chromium, manganese, iron and so on so on. But in the right hand side, extreme right, you will find non-metals: helium, neon, argon, sulfur, oxygen, fluorine, chlorine, bromine, iodine, astatine and so on so on. But between the metal and non-metal, that is left hand side and right hand side, there are some other elements which have the characteristics of like that of metal as well as non-metal. So they are called metallize. I think I am clear where the metals belong to. They belong in extreme right hand side and this side, and extreme right hand sides are very active metals, and this right hand sides metals but not so active, that of like that of the extreme right left hand sides. So today I am going to describe about the reactivity of these metals which are in the extreme left hand side. Okay, for example, you can take lithium, sodium and potassium, and I will show you the electronic configuration of lithium, sodium and potassium also here. Lithium 2,1 electronic configuration, sodium 281 and potassium 2881. That means when you go down in the group, that is moving from top to bottom, there occurs the increasing of one cell in every element. For example, 2 cells are there in lithium, 3 in sodium, 4 in potassium. I will show you another chart also. You see this, how this atomic size occurs. Atomic size of lithium, sodium and potassium. And this is nucleus, first cell, second cell. Nucleus, first cell, second cell, third cell. Nucleus, first cell, second cell, third cell and fourth cell in potassium. This measurement I took somehow equal for the respective cells. Nucleus of all these atoms are equal. First cell of all these atoms are equal. Second cell of all these atoms are equal. There is one more cell in sodium than that of the lithium, and there is 2 more cells in the potassium than that of the lithium, but 1 more than that of the sodium. So this is the electronic configuration. You can see that the distance from the nucleus to the outermost electron of this atom means lithium, is this distance, and here you see it is relatively bigger because the distance from nucleus to outermost electron here it is in the third cell, outermost electron here in the fourth cell. So this is the greatest distance, this is the middle distance, and this is the least distance. But when we talk about the reactivity, this is the main important things. They have one electron in their outermost cell. They have tendency to lose the electron to get stable configuration, because I already described their metals are electropositive. Now, how the reactivity occurs here? First of all, you see what happens. Atomic size increases due to the addition of cell. As you have seen, there is a addition of cells. Sodium has one more cell than that of lithium. Similar, the first point, that is increasing atomic size results the decreasing of force of attraction between nucleus and outermost electron. That you know that force of attraction is inversely proportional to the square of radius of this, or square of radius of that distance. Okay. Now, similarly, so bigger this atoms electrons or outermost, bigger the atoms, outermost electrons are more free. That bigger the size of the atom, the electrons are more free, because there is more distance. More distance means less force of attraction, and that results tendency of losing the valence electrons of bigger atom is more. So from this example, what we can conclude is less atomic radius, so the more force of attraction is there, and this lithium outermost electron is bind with a greater force, but sodium it is a little bit bigger, and it is the outermost electron is bind with the nucleus with a less force than that of potassium, but it is more, but it is less than that of sodium. I mean, due to the greater distance of potassium from nucleus to outermost electron, less force of attraction is there, so it can lose this electron easily. But here, with respect to potassium, I am comparing the reactivity of sodium with respect to potassium. Here is less distance. Less distance means more force of attraction. It is bind with a greater force than that of the potassium. So this electron, it can't lose easily like that of in the potassium, so that the potassium get stable configuration faster than that of the sodium. That's why potassium is more reactive than that of sodium. But if you compare the sodium with the lithium, then you will find there is less distance between the nucleus and outermost electron of lithium, and here more distance between the nucleus and outermost electron. So this electron is more free. I mean, sodium's outermost electron is more free, then it can lose that electron easily. Then sodium gets stable configuration faster or easily than that of the lithium. That's why sodium is more reactive than that of lithium. So let me conclude these things one more time. When you move from top to bottom, lithium, sodium and potassium, atomic size increases the atomic size, there is less force of attraction. Less force of attraction means the outermost electrons are binds with a loose force, so bigger the size, easier to lose the electron, smaller the size, difficult to lose the electron. That's why potassium lose electron faster than that of lithium. So potassium is more reactive than that of sodium, or sodium is more reactive than that of lithium. Thank you very much.